In this video, I'm going to discuss how to calculate the lengths of curves in curved spaces using the metric tensor. I'm also going to cover the differences between extrinsic and intrinsic geometry. If you haven't seen my first two videos on the metric tensor, I would highly recommend you check the links in the description and watch those first, since this video is going to build on the concepts from those videos. Also, if you're interested in learning more about the geometry of curved spaces, you can check out this professor's course notes on this website, which is also in the description. In particular, the Surfaces Part 2 PDF talks about the metric tensor, which is also called the first fundamental form. So if you've watched the previous videos, you'll already know how to use the metric tensor to get the lengths of vectors, and how to compute curve lengths in flat space. Now we're going to talk about curve lengths in curved space. So some examples of some curved 2D spaces are these 2D surfaces here. We have the cylinder, the hyperbolic paraboloid, which is sort of like a saddle shape, and we have the sphere. And in this video, we're going to be focusing on the sphere. So the first question to ask is, how do we describe a 2D surface mathematically? Well, the most common way is to start with the flat 2D plane with UV coordinates and put the UV plane through some sort of function which will stretch and transform the plane so that it becomes a 2D surface living in 3D space. Basically, we take every UV point in this plane and assign it some coordinates in 3D space, given by capital X, capital Y, and capital Z. So as an example of that, let's take this UV plane here, which has an image of my YouTube icon on it, and put it through the function to map it onto a sphere. So you can see that the V coordinate lines, which are the horizontal lines, end up being curves of latitude on the sphere, and the U coordinate lines end up being lines of longitude on the sphere. So this is very similar to taking a flat map of the Earth and stretching it and bending it so that it becomes a spherical globe. The flat map lives in the UV plane, and the resulting surface lives in XYZ space. So in order to do this transformation, we need to determine the three equations for X, Y, and Z. So for this example of the sphere, the transformation equations are here. And these might look a bit complicated, but if you look at this Z equation, Z is equal to cosine of U, this is basically saying that the U curves are the lines of longitude. So if you remember the graph of cosine, when U is equal to 0, cosine of U is equal to 1, which is up here at the North Pole where Z is equal to +1. And as we increase U all the way to pi, we end up decreasing cosine of U all the way to -1. And Z equals -1 is at the South Pole here. And you might think that the X and Y formulas look complicated, but remember, X is equal to cosine of V and Y is equal to sine of V are just the equations of a circle in the XY variables, right? Well, you can think of these equations as just giving the equation of a circle whose radius is sine of U. So remember with the graph of sine of U, at U equals 0, which remember is at the North Pole, we have a circle of radius 0, so that's just a point. And then as U gets bigger, we end up with the radius getting bigger, until we get to the equator at U is equal to pi over 2, and then we shrink down again to a point at U equals pi. So now that we have the equations for a spherical surface, how do we draw curves on the sphere? Like if I have some path on my map in the UV plane here, how do I move that path into XYZ space? Well, basically we take the equation of the path in our UV plane and just put it through this function so that it gets stretched and transformed into a path living on the 2D spherical surface in XYZ space. So if I have this path here going from Alaska to Singapore, we just put it through the same function and we end up with a path drawn on our 2D surface. So let's try that out for the sphere. Let's take this really simple path that takes a path parameter lambda and maps it to the point U equals lambda, V equals lambda in the UV plane. So this is just a diagonal line where the U and V coordinates are equal at all points, like this. And to put this path through the function here and move it onto the surface, we just sub in U is equal to lambda here and sub in V is equal to lambda here. And so we end up with these equations here, and that would result in a path on the sphere that looks like this, right? You can see how the path in the UV plane is sort of cutting diagonally across the grid line squares. And we would just do the same thing on the sphere and make the path cut diagonally through the grid boxes of longitude and latitude. And remember, if we want to get the length of this curve, the key to getting the lengths of curves is to use the magnitude of the tangent vector dr by d lambda, where r is just the position vector of a point on the curve in xyz space. So to get the arc length, we need to compute the magnitude of this tangent vector dr by d lambda, and we can get the squared magnitude by taking the dot product of the tangent vector with itself. So we can expand out this tangent vector in xyz space using the multivariable chain rule like this. And so we have a sum of 3 terms dotted with a sum of 3 terms. So in total, expanding out the dot product, that gives us 9 terms. And you might think this looks really ugly, but remember that since the xyz basis vectors are orthonormal, any of the dot products where the basis vectors are different, like x dot y or y dot z, those dot products go to 0. And any dot products where the basis vectors are the same go to 1. So we're left with a really simple formula here, just the x component squared plus the y component squared plus the z component squared. So this formula that we're using here, it's really just like Pythagoras' theorem for 3 dimensions, x squared plus y squared plus z squared. So we already have the formula for the path on our sphere in terms of x, y, and z, so we can compute the derivatives of x, y, and z with respect to lambda. So dx by d lambda can be found using the product rule, and it ends up being negative sine squared plus cosine squared. And by a well-known trig identity, this ends up being cosine of 2 lambda. Likewise, dy by d lambda can be found using product rule, and it ends up being 2 times cos times sine. And by another trig identity, this just ends up being sine of 2 lambda. And finally, dz by d lambda is just negative sine. So plugging all that in for our formulas for the squared magnitude of the tangent vector, we see that we get cosine squared plus sine squared, where the argument in both is the same, 2 times lambda, so all of this becomes 1. And so the formula we get is 1 plus sine of lambda squared. So we can try taking this integral from lambda equals 0 to lambda equals 1, but it turns out that the antiderivative of the square root of 1 plus sine squared is actually pretty difficult. So I'm just going to go ahead and cheat here by using Wolfram alpha, and you'll see that the arc length is about 1.12389. And this is interesting because it's not equal to the square root of 2, which is what we might have expected if we had measured the length in the UV plane using the normal Pythagoras' theorem formula. But remember, since this curve doesn't exist in flat space, we can't use this line of thinking. So what we really did when we calculated the arc length is we worked in 3D space and used this big giant formula to get the squared magnitude of the curve's tangent vector. And this big ugly formula can also be written as this series of array multiplications, where this matrix of basis vector dot products is the metric tensor. And since we're working with the 3D orthonormal Cartesian basis, this metric tensor is really just the identity matrix. So what I really want you to realize is that to compute the arc length, we were working in terms of the x, y, z coordinates. In other words, even though we were analyzing a 2D surface, we were working in the 3D space around the surface in order to understand it. And this approach to studying surfaces is called extrinsic geometry because it involves analyzing curved 2D spaces like the sphere using the surrounding 3D space that the surface lives in. But there's also another way to examine curved spaces, and that's by analyzing them without looking at the surrounding space. So in other words, instead of looking at the XYZ space, we would only be looking at the UV plane. And this point of view is called intrinsic geometry because we only focus on the curved space itself and not the surrounding space that it lives in. So if you like, you can think of intrinsic geometry as a bit like studying the Earth's surface from the perspective of a tiny person living on the Earth, rather than looking at the Earth from outer space. So to look at things from the intrinsic point of view, instead of expanding the tangent vector in terms of x, y, z, which are the coordinates of the surrounding space, we'll instead expand the tangent vector in terms of u and v, which are the coordinates of the curved space itself. So when calculating the squared magnitude of the curve's tangent vector, we would now expand the dot product in terms of the u and v variable. And expanding that dot product gives us this formula with 4 terms. And we can also write this more nicely using this series of array multiplications like this, where this matrix here is now our intrinsic metric tensor for the surface. So this is the metric tensor that we're going to use to compute the lengths of curves on our surface, and sometimes as an alternative to the derivative notation for the basis vectors, we can also use the EU and EV vector notation like this for the basis vectors instead. So using that notation, the metric tensor would look like this. And remember, these EU and EV basis vectors are just the tangent vectors along the U curves and the V curves on the surface. So at this point, the tangent vector along the U curve would look like this, and the tangent vector along the V curve would look like this. And at this point up here, the U tangent vector would be this, and the V tangent vector would be this. So notice how the basis vectors can sometimes change size depending on where we are on the surface. So let's compute the components of this metric tensor for the sphere. So recall that these are the equations that map the UV coordinates into 3D space for the sphere, which has radius 1. Now we can expand these tangent vectors dr by du and dr by dv in terms of the 3D Cartesian variables x, y, z using the multivariable chain rule like this. So if we calculate these components dx by du, dy by du, and dz by du, we get these formulas here. Basically, after differentiating, this sign becomes a cosine, and this sign becomes a cosine, and this cosine becomes a negative sign. And likewise, we can also compute dx by dv, dy by dv, and dz by dv to get this, where this cosine becomes a negative sign, this sign becomes a cosine, and this term just goes to 0 since there are no v variables in it. And I'm going to rewrite these formulas using the vector notation instead of the partial derivative notation. So we're now ready to compute the metric tensor using the basis vector dot products. So let's start with EV.EV. We can plug this formula in, and expanding out the dot product gives us these 4 terms. And the x.y and y.x terms go to 0 because the basis vectors are orthogonal, so we're left with these 2 terms, and of course x.x and y.y go to 1. So we're left with sine v squared sine u squared plus cos v squared sine u squared. So we can factor out the sine u squared term, and the sum of sine squared plus cosine squared with the v variables goes to 1. And so we're left with just sine of u squared for the v basis vector dotted with itself. Now for the u.u term, I'm going to skip all the cross terms that involve x.y, y.z, and x.z, since they all go to 0 anyway, and just give us the terms that we care about. So basically, this component squared plus this component squared plus this component squared. So we can factor out the cosine of u squared from these 2 terms and get this, and again, cosine v squared plus sine v squared goes to 1. And yet again, cosine u squared plus sine u squared also goes to 1. So we get that the dot product of the u basis vector with itself is just equal to 1. Finally, we'll compute u.v, which is the same thing as v.u. And again, I'm ignoring the cross terms, which all go to 0, and just focusing on the terms that we care about. So we get this times this for the first term, and this times this for the second term, and this times 0 for the final term. Obviously, this third term goes to 0, and the 2 remaining terms are actually the exact same, except one is positive and one is negative. So they end up canceling out and we get 0. So the metric tensor we're looking for looks like this. v.v equals sine of u squared, u.u is equal to 1, and the cross terms u.v and v.u go to 0. So with this equation of array multiplications for the squared magnitude of the curve's tangent vector, we just computed the elements of this metric tensor here, which are the basis vector dot products, and so we got this. And so multiplying all of that out, we get this expression here, which is sort of like Pythagoras' theorem, but we have this extra multiplying factor here of sine of u squared. So let's once again compute the length of this diagonal path given by u equals lambda and v equals lambda. And remember, this actually represents a path on the sphere that looks like this. So we have this equation that we derived for the squared magnitude of the curved tangent vector using the metric tensor components. And this is the path we care about. So in this case, du by d lambda and dv by d lambda are extremely easy. We just get 1 and 1. So plugging 1 into here and 1 into here and lambda into here for u, we get this, which is really just 1 plus sine of lambda squared. And if you recall, this is exactly what we got before using the extrinsic approach with the x, y, z variables. So again, this integral is pretty hard to do by hand, but giving it to Wolfram alpha, we see once again that the answer is about 1.12389. So using this intrinsic approach, notice that the formula for the squared magnitude of the tangent vector only depends on the u and v variables. It doesn't make any reference to the surrounding x, y, z space. And again, this looks very similar to Pythagoras' theorem, c squared is equal to a squared plus b squared, except we have this extra sine of u squared part attached to the v component term. So what exactly does this part mean? Well, this part is telling us that the way we measure distance in the v coordinate direction changes depending on where we are on the sphere. So I'll show you what I mean by that. Let's take the path with the parameterization u is equal to pi over 4 and v is equal to lambda. So in the UV plane, with this map of the world, that would correspond to this path here. And on the spherical Earth, this would be traveling along this line of latitude. So if we try and compute the length of this curve along 1 unit of lambda, we start with the metric equation here. So du by d lambda is equal to 0, and dv by d lambda is equal to 1, and u is equal to pi over 4, so we get this. And since sine of pi over 4 is equal to root 2 over 2, that squared is just 2 over 4, or 1/2, which is the squared magnitude of the tangent vector. And if we compute the length of the curve over 1 unit of lambda, we get a total length of the square root of 1/2. Now we can try going through that exact same exercise again, but for u equals pi over 2. So that would correspond to this path here in the UV plane, and this line of latitude here on the globe at the equator. So we can go and plug all these values in again, and now sine of pi over 2 is just 1, and 1 squared is just 1. And churning through this integral for 1 unit of lambda, we get a length of 1, which is longer than what we got before, where we got the square root of 1/2. So what we just showed is that along this curve number 1 and this curve number 2, even though they look like they're the same length in the UV plane, they actually aren't the same length. And that's because this curve is at a higher latitude, meaning it would be shorter than this curve, which is on the equator. So even though the curves look like they're the same length in the UV plane, we have to remember that the rules for measuring distance change from point to point in curved space because of this sine of u squared term here. Okay, so we've learned that in curved space, you can't trust your eyeballs to measure distance. If you want to measure distance properly, you can only trust the metric tensor, because with curved geometry, our eyes will get a distorted view of distance. And this is exactly what we see when we look at flat maps of the Earth, right? Like here, we have a projection of the Earth onto the flat plane. And I should mention that this projection also involves distortions in the north-south directions that we didn't see in our previous example. But my point is, we all know that maps like this distort the sizes of countries, right? Looking at this map here, we might think that Greenland is really big and Australia is really small. But if we drag Greenland over, showing its actual size next to Australia, we see that Greenland is a fair bit smaller. And likewise, if we drag Australia up here while preserving the size, we see that it's bigger than Greenland. So the reason for all this geometric distortion is because the space we're in is curved, and that means that the rules for measuring distance change from place to place. In other words, the metric tensor is changing from place to place. And that means that we have a metric tensor field. So you know that a vector field involves vectors placed everywhere in space that change from point to point. And you know that a covector field involves covectors that are placed everywhere in space that change from point to point. And now a metric tensor field involves a different metric tensor being placed everywhere in space that change from point to point. And every curved space, whether it's the sphere or the cylinder or the saddle, every curved space has its own metric tensor field associated with it that gives you the rules for measuring distance on it. And you can try computing these metric tensors for yourself if you like, using these equations to get the u and v tangent vectors. So in summary, there are two ways of looking at curved spaces. There's the extrinsic view, where we view the surface as living inside the surrounding space, the XYZ space, and this is sort of like a bird's eye view where we look at the surface from far away outside. And then there's the intrinsic view, where we're only allowed to talk about the space itself, without reference to anything outside. In this case, we use the UV plane. And this is sort of like a bug's eye view for a bug wandering around the surface that has no idea that an outside space exists. And in the extrinsic view, we expand the tangent vector using the Cartesian XYZ variables and get this metric tensor. And for the intrinsic view, we expand the tangent vectors using the UV variables and get this metric tensor. And we can also write the metric tensors using this vector notation. Now, if we change the variable names and use u1, u2 instead of u and v, and use x1, x2, x3 instead of xyz, then we can write the metric tensor equations a lot more easily using Einstein notation. We can expand the vectors like this with implied summations, and write the metric tensor components like this using the dot products. And we can write the formula for the squared magnitude of the tangent vectors like this in both cases using the dot product. And we can replace these dot products of the basis vectors using the metric tensor components and summarize the metric equations compactly like this. Now, the last thing you might be worried about is that in our intrinsic geometry, we're still making use of the r position vector, and the r vector lives in 3D space, which means we're making reference to the space outside our curved surface. So what mathematicians often do when they want to stay completely intrinsic in the surface is they just remove the r vectors from the equations completely and treat the derivative operators themselves as the vectors. And if this confuses you, I'd encourage you to check the link in the description for more information on why derivative operators can be viewed as vectors. But the main takeaway of this video is that when we study surfaces intrinsically, they all have their own metric tensor field that gives you the rules for measuring distance at various places in the curved space.